Hello and welcome back to the lab. Continuing on with this 475A. This is going to be the vertical section. I've got the scope set up as required on the front end. Everything's had a appropriate warm-up time. I've got the 6500 on just in case we need it. The Rigel's on. The 106 is on, and the TM 5006 with all the scope calibration gear in it, because this is going to use extensive use of the 106 and the PG 506. First step up, we need to adjust the vertical output bias for the smallest signal, that is our 488, which is hiding back on the actual vertical amplifier board right here on the side. So we'll get down on there, being careful not to get zapped or short anything out. And let's see here. And we are actually adjusting for a maximum display. So, as we rotate, I can make it smaller. And gone a little far. Zoom in here real quick and use the camera to cheat. Alright, we will use the camera to cheat. Right there, that's maximum. Okay. Next is the shield voltage. Okay, there's a thick film resistor network that's hiding back under here. Here's the back of where the resistor goes. There's a top plate that goes on top of this that I have removed. There's a top plate that covers this section. It's right over there. And so I'm letting this set. This is one of those measurements where having a second meter is very important, because balancing this out with a single meter is tedious to the extreme. So I'm waiting on the DM 502As to warm up completely so they get into spec, but they're hooked up. So we'll let this just cruise for right now, tubes off, and let everything come up to temperature, and then we'll just double check our results. Okay, so we have balanced voltages on this particular unit. This isn't going to be true for any unit, but this particular one, that's where the beam position is. Okay, here's our test setup. Picking up a ground down here. Test point 1395 is way up top up here, and we're looking at a voltage within a half a volt of the recorded voltage in part C. Our recorded voltage in part C was 34 or 33.9 depending on the deflection plate, and we are getting 33.9. That is perfect, so no adjustments needed on the shield voltage. Okay, next up is delay line zeroing. So we're going to pick up the delay line out here on this side of the scope, and I measure the delay line to each other, and then we measure the delay line to ground, and we should end up seeing 0. These hooks are a bit long, so I'm going to switch out my meter leads to this style, which is easier to hook up. And let's grab some delay line pins. Okay, we're now hooked up to the delay line. Those were almost too big, so shrinking those, getting some pin grabbers may have been a little bit easier, but we're going to adjust channel 1 for a reading of 0 volts on the meter. Keep an eye on the meter for me. Can't ask for better than that. We're at half a microvolt for 0, so good enough for me. So switching in real quick, just a ground clip, and then, well, that's not good. So we need to adjust our 385 delay line centering for 0 volts. And that's rather conveniently placed. This is the resistor we'll be adjusting. It's at the top of the board, up on the side. It's moving nice and fast. This was not a large adjustment, but we'll call it right there. That's going to be good. Okay, checking the DC balance of channel 1, variable DC balance. We need to be at the center of the screen. Now, when we pop out of the alignment detent here, we don't move, which is good. And we'll run this through the range. And that's moving a little bit. So what we will do is we will adjust R110 for a bit. Where are you, R110? R110 is actually right here on the bottom side underneath the attenuator, or right at the back of the attenuator. So this is kind of a fiddly adjustment because you can throw it pretty far out of whack quick, like just like that. Okay, we have located a fault in the vertical board. The scope's been going out to lunch and it's been arguing with me. But as you can see right here, how it's flexing. But also if I come down here, that is a horribly intermittent connection. So, it was getting warm enough where the whole thing was just kind of crashing out and falling out. Trigger would stop. Everything would kind of fall apart. And the scope would just go out to lunch. However, it is very much looking like, because if I push on the main amplifier, nothing. Channel amplifier, nothing. It's also affecting both channels too. Second channel amplifier, nothing. However, if I'm down by these TI sockets, flexing the board down there, I can almost get it to crash out and go away. This is supposed to be a 20 millivolt signal. Obviously, our gain is way low down here, so I believe we have found at least an issue, if not one of the issues. And I'm pushing on the board in this section down here. So like if you guys can see the screen, if I just poke this IC, I can make it, this one actually, make a move. There we go. There's our connection. So it's probably this IC socket. The IC is good, I'm sure, because the scope is working intermittently. But I either have a cracked solder joint in this general area, or I have it's not the finger switches that are moving. Wait a minute. Okay, now I tap this finger switch, and we're back. We may have dirty finger switches. That wouldn't shock me. It's a piece of tech gear. All right, let me clean these switches up. What are these in? Those are in. Oh, those are in the trigger view circuit. Okay. Well, that would make sense because I'm losing trigger 2. So before we do anything drastic, let's clean up these finger switches, and we will go from there. Okay, we've got our variable DC balance set back in. Moving this from one end to the other. Trace barely moves, so we are set there. I also got the issues with the trace blanking squared away. Those ended up being some switches on the back side of the vertical board when I turned the scope. Actually, let me just do that now. So, problems I was having was these two switches back here, which is the trigger view, and then this pack of switches right here, which is the bandwidth limit. I cleaned all these switches up, and I reseated these 3 ICs for good measure, and I let the scope run for days and days and days. Triggered on a waveform, obviously not running the tube, because when the error would manifest, the trigger light would go out, so I could monitor it that way. And it was fine. It never lost trigger. Everything was good. So we're back into alignment territory. Okay, for step 12, which is the volts per division balance, we should have less than half a division of drift when switching from 10 to 5. That is actually perfect. And it wants us to do the same check on channel 2. And that is perfect there. And also we'll check the variable. And the variable on 2 is dead on. It's perfect. Invert balance is perfect as well. That was just checking for trace movement. So that doesn't even need to be adjusted. AC. We're going to need a 50 ohm terminator and some wire. Because I'm going to need 100 megahertz of signal. Five. And a little bit more signal. I want 6 divisions of display, which is fine. Okay. So we turn this all the way down now. There is plenty of positioning control, so that is fine. Have to move this up to channel 1. AC. Channel 1. Need a little more signal. Plenty of positioning control on channel 1. Alright. I want to check AC/DC ground switches. AC works. Ground works. DC works. Same test on channel 2. AC works. Ground works. DC works. All right. Okay, gonna check indication. Here's just a random probe with an indicator pin and our light transitions. So indication's working. Indication on channel 1 is working. So we are good there. Channel 1, 5 millivolts. Okay, well, it's gone out to lunch again. So, ran fine for 3 days, and now it's back out to lunch. This time, though, I think my problem is actually over on the trigger board as opposed to the vertical board, because the trigger board, it looks like, isn't even firing a sweep. Checking it on a different scope, I am not getting any gating pulses. So, let's dive around the trigger board, see what we find. Okay, well, we're in the deep end now. So we're going to start with removing Q572, which is right here. And what that should do is that should make it so I at least have a sweep. Let's see what happens. We still do not have any sweep. So let's check 572 real quick. Oh, it says it's a Darlington, so at least identified the part. So let's see what we've got. Here's my first transistor of interest. Now, how am I going to test this thing? Let's see. I don't know if you guys can see that, but given the scope enough time to cool down, trace comes back. So now for sure we have something that's thermal. So now the question is what? Bad solder joint, socket, pissed off diode, pissed off transistor. There's a lot of options it could be. So I'm actually going to turn on the nitrogen iron and wind that around like a hot air gun, warm up some parts, see if I can't get it to fail, give me an idea where this problem issue might be. All right, I've got the timing board out, So I'm going to really inspect this for cracked solder joints, things like that. Last night, the fault proved itself to be 100% thermal. But it's also a long fault. So what's going on is the scope's got to warm up for a couple of hours. The room temperature's got to get hot. Sweep dies. Then it's got to cool off for about 30 minutes. Then it comes back. So it's a very long fault. Very strange. What's on the list here is checking this board for cracked solder joints. I have a I got some information asking some things on the online group. If the there's some transistors that are suspect on here. There's a specific part number. I'm working on dialing up a testing procedure for those. That way we'll know if I can test it. I've tested one, but it didn't test the way I expected. So I do have some 20-pin sockets, which I'm going to need for this chip. So I'm going to get that. I'm going to warm up the irons. We're going to get that swapped out. I'm going to really inspect this for cold solder joints, but I am pretty sure the fault is on this board. Now, while we have the scope open, I'm also going to service the timing switches and things like that because I have good access to them right now. Okay, I've got the scope reassembled. Obviously, it's working. After pulling the sweep board, looking over that for cold and dry solder joints, I found like one or two, nothing really major. I did replace the already known failure TI socket on the sweep chip. The other two trigger chips, they had the inboard sockets, so they were fine. I did a video for those that are joining the channel right now. I did a video on specifically why these sockets, these specific TI sockets, are terrible. TI makes some good stuff. This was just a bad design, and there's a video in the library that goes in depth into why that is. So what I got to do now is, because this was such an intermittent fault, I'm actually cautiously optimistic about this one. I have a very low-level sine wave going in. The flipping is not a trigger problem. It's a sweep speed issue. Now, for the eagle-eyed, in the previous video when I was going through the calibration, I was playing with these two switches, just trying to clean up the waveform because it was giving me some trigger glitches. It wasn't stable. It would just flip and then come back, and then flip and then come back, and then flip and then come back. I attributed that to the scope being open. My lab is a very noisy environment. I do not have a Faraday cage to do alignments in. That is probably something I will have to look into in the future, building a electrically quiet room to do some very sensitive measurements and alignments in. But I attribute that to a false trigger for high frequency. So if I would set it to like high frequency reject, it would get better. And then if I would set it to low frequency reject, it would get a little better. So I thought that was a false trigger. That may have indicated a fault because I cleaned these switches. I cleaned the timing switches and serviced the cam. And this is much more stable. I'm not seeing the trigger glitching or anything like that. So my next step is to get this nice and warm, make sure we still have triggering. I can do all that testing long term because I can just watch the trigger light when the fault arises. It just kind of goes out to lunch, and the trigger goes completely out and the sweep's dead. So as long as I have a trigger light, we're good to go. So I'm going to let this run for most of the rest of the day. I didn't want to burn the 106 for that long, just for the life of the tube, so I got it hooked up to random function generator. We have a small bit of signal going in because that'll indicate sooner. The smaller the signal is, the harder the trigger circuit's got to look to find it. So if it was full division, that'd be a lot of signal to trigger on. And it's actually easier for the scope to trigger on that than it is to trigger on a small signal. So cautiously optimistic at this point because I'm not seeing that trigger glitch, and this is nice and stable. So I'm going to let this run. We'll see how it goes. But I got to put time on it. So I'm going to cut this video here. We will be back to revisiting this 475A. Given the condition, I do not want to give up on this scope. I really want to fix what's going on with it. I do have some indications that the transistors might be leaky. When I get some more information on that, I'm going to put out a specific video on doing the transistor leakage testing, and then we will go from there. And I have a couple of things in the lab that I can use for leakage testing. The 577, the SMU, and even the Keithley can do some leakage testing. So all will be good. But with that, I will see everybody in the next video. And as always, more is on the way. So stay tuned.